This video is part 1 of Involutive Heegaard Floer homology and surgeries. This project is joint with Kristen Hendricks, Jen Hom, and Matt Stoffragan. In this talk, we'll talk about background and motivation for our results and then state our main results. In part 2 of the talk, we'll discuss a few aspects of the proof and also describe some, give a practical guide to using some of our results. Okay, so we're going to begin with some background on Heegaard Floer homology. If Y is a 3-manifold equipped with a spin C structure, Oshvath and Szabo created these 3 related F adjoin U modules as HF minus, HF plus, and HF infinity. They constructed a refinement for knots in 3 manifolds, which the refinement takes the form of a chain complex, CFK infinity, which has a filtration by Z plus Z. Here's an example for the trefoil in this picture. Each dot represents a generator over the ring F. Each arrow represents a differential, and the grid represents the filtration level of a generator. Oshvath and Szabo proved a very powerful relation between the 3-manifold invariance and knot Floer homology. So they proved, and one of the relations they proved was this mapping cone formula, which says that if you have a knot in a 3-manifold, which let's just say is an integer homology 3-sphere for simplicity, then HF minus of the end surgery of this knot is equal to is quasi-isomorphic to the mapping cone of a map from 2 complexes defined using knot Floer homology. We'll talk a little bit more about exactly what A and B are, but the main point is that they're defined using knot Floer homology. A and B are essentially subcomplexes of CFK infinity, and the map Dn is for a knot in S3 is just defined in terms of inclusions of subcomplexes. But in general, it's just some chain map that might require additional holomorphic curve counts. Here in the formula, we're working over HF minus, and for the formula to work, we also need to use the power series ring. We need to use coefficients in the power series ring obtained by completing over the variable u. And as I mentioned, when Y is S3, this map Dn is completely computable just from the homotopy type of this complex CFK infinity. In general, for an arbitrary 3-manifold, it might require more complicated holomorphic curve counts. There's some maps that might not be computable just from the complex, but for knot in S3, it's always computable just from the complex. And let's say a little bit more about this formula. So in the formula, this A, it's a direct product of these A sub S complexes, and B is also a direct product of B sub S complexes. So it's an infinite, they're both infinite direct products. And these are AS and BS, these are complexes, finitely generated complexes over F adjoin U. And actually they're subcomplexes of CFK infinity. And we're using this, the bold face indicates that they have coefficients in this power series ring F adjoin U. And the map Dn decomposes as V plus H, where both V and H both have a very predictable shift in the indices. So A sub S and B sub S, we can sort of schematically indicate that they take this forms like this. So A sub S is a quadrant, takes the form of all the generators which have filtration level in a certain quadrant, and B sub S consists of all the generators which have filtration level in a certain half plane. And actually, so A sub S clearly depends on S in the sense that it's everything below the line J equals S. But B sub S actually doesn't depend on S. The S is just an index. We have infinitely many copies of it appearing in the formula. And actually, the homology of B sub S is just the homology of the Heegaard Floer homology of the underlying 3-manifold. So sort of a little even bit more concretely, we have the mapping cone formula. Here's an example when n is equal to 1 of its structure. So the V maps just preserve the index. They go from AI to BI. And the H maps increase the index by 1. They go from AI to AI plus 1. So you obtain sort of a complex that has this form. In this case, you have sort of this zigzag shape. And actually, so the cone formula also works for HF plus, but the formula uses direct sums instead of direct products, and you don't need to complete over the ring F adjoin U. So algebraically, it actually is a little simpler over for HF plus. We've stated it for HF minus, though sort of as long as you take these small algebraic modifications, it's basically formally the same. So this is one of the motivations for our talk, and now we're going to enter the world of involutive Heegaard Floer homology. Involutive Heegaard Floer homology was introduced by Hendricks and Manolescu in 2015. If we have a three-manifold Y with a spin C structure that is self-conjugate, so a set of spin C structures on Y has a conjugation action, and we want to consider one which is fixed by the conjugation action. Hendricks and Manolescu constructed a homotopy involution iota from CF minus Y to CF minus Y in a spin C structure S, and it's constructed as follows. We take a Heegaard diagram sigma alpha beta, and there's a canonical isomorphism between the Floer homology of CF minus of H bar with CF minus of H, where H bar is the Heegaard diagram obtained by reversing the orientation of sigma and reversing the roles of alpha and beta. H and H bar are both Heegaard diagrams for the same three-manifold, and there's this canonical isomorphism between the Floer homologies computed with respect to these diagrams. So in fact, there's just a bijection between the generators of the complex, and eta just extends this bijection linearly, and this turns out to be a chain isomorphism. There's also a map from naturality relating CF minus of H and CF minus of H bar. And the map from naturality is obtained by picking a sequence of Heegaard moves which connects H and H bar. These might be stabilizations or handle slides or isotopies. But by picking some sequence, we can obtain a map we can obtain another homotopy equivalence from CF minus H to CF minus H bar. And if we compose this map CH to H bar, we compose it with eta, we get the map iota. And the map iota is a homotopy involution. It squares to the identity up to homotopy. So the involutive Floer complex, CFI minus, is defined as the mapping cone of 1 plus iota. And 1 plus iota, and so in this formula we have this Q variable added in, and that's just kind of formally added into the mapping cone complex, because if we do this, we can actually view it as a module over F adjoin U, Q mod Q squared, where the action of Q takes the domain of the mapping cone to the codomain. And this has had applications to the homology cobordism group. For example, there's this recent paper of Dihom, Stoffregen, and Trong, which proves that there's an infinite, there's a Z infinity summand of the homology cobordism group using involutive Heegaard Floer homology. Their proof went by way of constructing an infinite family of homomorphisms from the homology cobordism group, defined using involutive Heegaard Floer homology. So it sees a lot of information about the homology cobordism group. But here's a question: how do we compute HFI minus? So, for example, is there an analog of the mapping cone formula, which we talked about earlier, which exists for ordinary Heegaard Floer homology? So let's talk about some previous results towards computing involutive Heegaard Floer homology. Hendricks and Manolescu defined a refinement of their involution, which for not Floer homology, they defined a not involution, iota k, from CFK infinity k to CFK infinity of k. And they use this to compute the involutive Heegaard Floer homology of large surgeries. So they proved that if the surgery coefficient is large enough, and you have a knot in a, let's say, an integer homology 3-sphere, then the involutive Heegaard Floer homology of the surgered manifold coincides with the knot involution on A0, which is a subcomplex of C of k infinity. So A0 consists of, so A0 is just a particular subcomplex of C of k infinity. And they showed that sort of these are equivalent as complexes equipped with homotopy involutions. And so, in particular, if you wanted to compute the involutive Floer homology, this would be the cone from A0 to A0 of 1 plus iota k. And here, S0 denotes the spin C structure identified with 0 under an isomorphism spin C yn to Z mod n. Okay, so here's another. There's been more results concerning computing involutive Floer homology. So the hat version, HFI hat, has been completely computed. Can be computed algorithmically always, not just for surgeries on a knot, but just for any 3-manifold using bordered Floer homology. And this is due to work of Hendricks and Lipschitz. And also there's an exact sequence that they proved. They proved a surgery exact sequence. If you have a framed knot in a 3-manifold, then there's an exact sequence relating HFI hat y, HFI hat y0, HFI hat y1. And so this worked for any 3-manifold, but it only works for the hat version. The reason it only works for the hat version is because that's all that bordered Floer homology is currently computed for. So, but it does give a complete computation in that case. That's algorithmic. And it's been used to compute families of involutive Heegaard Floer homology. Okay, and so some more computational tools. There's a paper by Dye and Manolescu, which computes the involutive Heegaard Floer homology for 3-manifolds obtained by plumbing along almost rational graphs. This includes all Seifert fibered homology 3-spheres. And this, you can view this as an analog of earlier work of Oshwald and Szabo for ordinary Heegaard Floer homology. So Dye and Manolescu kind of proved an involutive version of a theorem that was known in the setting of just ordinary Heegaard Floer homology. And then there's other ways of getting computing the involutive Floer homology of new manifolds from old. So if you know the involutive Heegaard Floer homology of y1 and y2, Hendricks, Manolescu, and myself proved that the involution on the connected sum is computable. It's the tensor product of the involutions under the connected sum formula. So if you have the involution on y1 and you have the involution on y2, there's a formula for the involution on the connected sum. And then as sort of an analog of this for non-Floer homology, I proved that if there's a formula for the involutive Heegaard Floer homology, for the knot involution on a connected sum of knots, given the knot involution on the two summands. I haven't written the formula down here. It's a little bit more complicated than just the tensor product, but it's in the same spirit. But I guess the take-home message at this point is just that we have many techniques for computing involutive Heegaard Floer homology, and most of them actually have analogs in ordinary Heegaard Floer homology. But sort of the main one that we don't have is the mapping cone formula. We haven't proven the mapping cone formula for involutive Heegaard Floer homology. But that's kind of the point of this talk, is to talk about new developments towards computing involutive Heegaard Floer homology. So a first development, which is joint with Christian Hendricks, Jen Hom, and Matt Stoffregen, are the surgery exact sequences. So if you have a framed knot in Y, just any 3-manifold, then there's this exact sequence relating HFI minus of Y, HFI minus of Y0, and HFI minus of Y1. If you'd like, you could take HFI plus instead. The same proof will work. And Y0, so this is a knot that is framed. Y0 just denotes the surgery of Y along K with whatever your favorite framing is. And Y1 denotes just one framing higher. But if you have a knot in an integer homology 3-sphere, then there's sort of a canonical Seifert framing. So we also proved that if you're in this situation where it's a null homologous knot, I mean automatically since it's an integer homology 3-sphere, then there's an exact sequence but relating the n surgery, the n plus m surgery, and a twisted version of HFI minus of y. And so some comments just clarifying what these terms mean. The bolded coefficients denote coefficients in the power series ring, which is necessary since we're working with the minus version. And the underline denotes twisted coefficients. Okay, and then so joint with Kristen Hendricks, Jen Hom, and Matt Stoffregen. We've also proven this we've proven the involutive mapping cone formula. And so here I have the statement of the cone formula, but I have it sort of in a slightly weaker form, and in a weak form. So what we've proven is that if you have a knot in an integer homology 3-sphere, and you pick a positive surgery coefficient, then there's a homotopy equivalence. Well, there are maps dn, hn, and iota b fitting into this diagram on the right, such that there's also a homotopy equivalence between CFI minus yn of the n surgery of y along k and this diagram. This is slightly weaker because it doesn't tell you how to compute dn or hn or iota b. It just says there are some maps that fit into a diagram of this form that make the right side a chain complex and such that the left and the right sides are homotopy equivalent. So this is the weak form because it actually can help. You can actually use it to compute sometimes, but in general, it doesn't actually tell you how to compute things. It's not quite a robust way to compute. And so here are some first comments on the sort of weak form of the mapping cone formula. If you have an integer homology 3-sphere and you do n surgery on it, if n is odd, then there's one self-conjugate spin C structure on the n surgery, and this is the 0 spin C structure. Because there's a bijection between spin C structures in y sub n and z mod n. And if n is even, then there's actually two self-conjugate spin C structures. The involutive mapping cone formula actually naturally splits over orbits of spin C structures on the surgery. So you can naturally compute, the mapping cone formula naturally splits over orbits of spin C structures under the action of conjugation. And some more comments about the maps appearing in the weak version of the cone formula. Iota A is actually just always equal to the knot involution up to, say, some very predictable shifts in indexing. Basically just up to conventions, it's just equal to iota K on the nose. But for general Y, the maps iota B and H don't really appear naturally determined by just the complex CFK infinity YK and the knot involution. We would kind of expect them to require a greater understanding of, they would require more holomorphic curve counts. There's not a lot of rigidity like it in the sense that they're not really determined by just iota K, or that isn't our expectation. But there is a stronger mapping cone formula for knots in L spaces. So an L space integer homology 3-sphere, there's not very many. It's basically just S3, and the only other known one that I'm aware of is the Poincare homology sphere. But we'll just say L space, but really it's just knots in S3. So here's a stronger version of the theorem. If we have a knot in, let's say, S3, and you take a positive surgery coefficient, integral surgery coefficient, then the maps appearing in the involutive mapping cone are all computable completely from CFK infinity and the knot involution. And in particular, this homotopy type CFI minus YNK, the homotopy type over the ring F adjoin UQ mod Q squared is completely determined from CFK infinity iota K, and we give a fairly simple algorithm for determining it. Okay. And so we'll just say a little bit more about this. Basically, in this last statement, we had there's kind of this question of going from CFK infinity iota K and then filling in the maps dn and hn and iota b in the mapping cone. And so what we did was this is just a purely algebraic step, but if we took but we defined a correspondence between iota K complexes that have a certain special form and mapping cone complexes. We defined a map which takes an iota K complex, which that is particularly simple, and sends it to a mapping cone. We proved it was well defined. So I'll say a little bit more about that. So we'll say an algebraic iota K complex, which is just like it's just a complex that looks like it's equal to CFK infinity of a knot in S3. So an algebraic iota K complex is L space type if the homology B sub S, which is some subcomplex of CFK infinity, is F adjoin U. And so note that, like, if you have a knot in Y, the homology of B sub S is always HF minus of Y. So if this algebraic iota K complex actually came from, if it actually was the knot Floer homology of a knot, then saying it's L space type is just saying it's of a knot in an L space. So that's all that means. And so this is what we proved. This is just algebraic. We proved that there's sort of just an algebraic map that's well defined that sends an iota K complex of L space type to an iota complex. And it's the iota complex you get is sort of the cone, the mapping cone. And we proved that this is well defined on the level of homotopy types. So if you take two homotopic iota K complexes, you get two homotopic iota complexes. So this last theorem is just an algebra theorem. This doesn't have anything to do with Heegaard Floer homology. This is just purely algebra, but it's a nice framework for things to live in. And what we proved, the strong formula, the strong mapping cone formula, is that if I have a knot in an L space Y, basically if I have a knot in S3, and I have a positive integral surgery coefficient, then CFI minus of the end surgery of K is homotopy equivalent to this canonical model of the cone we built. And so in particular, CFI minus is just determined by CFK infinity, and we give an algorithm to compute it that's not that complicated. In the second part of the talk, we will describe actually how to compute this and what the canonical model of the cone is. But for now, we'll end the first part of this talk with an application. An application expands on the work of Dai-Hom, Stoffregen, and Trong, using their algebraic theory of almost iota complexes. And what we prove is that the homology cobordism group is not generated by Seifert-Fibert homology three spheres. Basically, we exhibit a three-manifold whose involutive Heegaard Floer homology is sufficiently complicated and doesn't lie in the span of complexes which have the sort of restricted form that Seifert-Fibert homology three spheres have.